Hi, and welcome to this section of the Calculus 3 tutor. And in this section of the class, we're going to switch gears a little bit from all of the vectors that we've been doing so far, and we're going to tackle the topic of double integrals, or double integration, okay? So when you flip to the back of a calculus textbook, usually you'll see these things called double and triple integrals, which we're going to get to here in the next several sections. And they can look off-putting at first. I mean, they can give you the creeps a little bit at first because, instead of just one integral sign, you might see two of them or you might see three of them. And you get into integration of different coordinate systems that we'll get into here in a little bit. But right now we're going to focus on double integrals. Let me ask you the following. Remember back in Calculus 1 when you first learned the concept of an integral, it's usually presented to you as the area under a curve, right? You have some function of x, f of x, and when you take the integral of that function between 2 points, along the x-axis, and you're integrating that function, what you're really doing is you're finding the area under that curve. Now we all know that integrals are used for things a lot more interesting than just finding the area of something. You flip over and open a physics text or any advanced text out there in physics or engineering or whatever, you'll find integrals everywhere. And it just turns out that integration is a really nice handy way of summing up an infinite number of infinitesimally small things. That's what integration is. So when you're doing lots of problems in real life with stress or strain in buildings or electricity and magnetism. I mean, the list goes on and on. Integration is just as core as anything goes. Okay, so we've talked up till this point in the course about the functions of 2 variables and the functions of 3 variables, and we talked about how to take these partial derivatives, which is a real slick way to take the derivative of the function in more than one direction or in different directions, okay? To see how the function changes as you look in different directions. That's what we were doing, okay? Now, how do you think we would actually integrate a function of 2 variables? Remember, a function of 2 variables sits on top of the xy plane. X and y are the independent variables. We plug them in and we get a third value. So when you draw these functions, usually they look like a mountain or something that's hovering right over the xy plane, okay? How do you think we would integrate that? What would we do that would be analogous to the regular integral that we do way back in Calculus 1 that was defined to be the area under the curve, okay? Well, turns out that when you're dealing with more than one variable functions, you're going to do double integrals, and later on we're going to do triple integrals. The good news is, and I do mean this one with all sincerity, okay, when you get comfortable with the material in this section, it's not going to be so hard to bite off the next section and the next section and the next section. You just have to wrap your brain around this section, and once you've done that and get really comfortable with it, then going on to the section afterwards where you're doing things slightly differently or triple integration, and there's several other things that we're going to do after this that are going to build upon this. It's going to make your life easy. So now that I've laid the groundwork for what we're doing and why we're doing it, and the fact that we're going to try to do some sort of integration stuff with the multivariable functions, okay, then we're going to go ahead and actually solidify it and learn something from it. So recall from the last DVD, okay, this is sort of something I just wanted to bring up just to kind of tie it all home. Recall from the last DVD, remember actually the first calculus DVD, this is the XY graph. There's nothing fancy, no three-dimensional functions going on here, okay? If I had a function that was defined to look, let's say, like this, okay? And if I were to take this function and rotate it around the x-axis, then I might get something that might look like this, right? I might get some sort of vase-looking thing. All right, and before we were interested in finding the volume of this thing. Okay, we were interested in finding the volume, and we actually wrote a formula for the volume, which was the integral from a to b, where this point was point A along the x-axis, and this point was point B along the x-axis, and it was the integral of pi times f of x squared dx, where this function here was f of x, and we took f of x and we rotated it around the x-axis. So what you were doing here is it's pi, because this is a function here and you're rotating it around, so you have a circular cross section everywhere you slice here. So if the radius of this function is actually going to be equal to f of x, because if you're looking at this vase, the radius from this point to here is going to be f of x all along here. Okay, so pi times the radius squared, pi r squared, is going to give you the area of a cross-section circle, right? So you chop it up at any slice, pi times f of x squared is an area of the cross section, and then doing the integration from a to b is what actually adds up the cross sections to give you the volume. Okay, that's what we were doing. Why do I bring that up? Because I just sort of want to give you the big picture about where we're coming from here. This only works for symmetrical objects. If you had a vase here that was nice and symmetrical, you could look and define a function and you could use this and calculate it pretty easily. But we all know real life doesn't have always have a great deal of just whiz-bang symmetry that's going to make our life easy. I mean, if it did, then things would be great, but it always isn't like that, okay? So, what if you had a function that was a little more complicated, or I should say an object that was a little more complicated, and what if I wanted to find the volume of that more complicated object? So what I'm going to do here is I'm going to put our x, y, and z coordinate system in place like I always try to do. Okay, and then the next thing I'm going to do is I'm going to say, what if I've defined a function of two variables, a function of x and y, okay? So this is going to be a function of x comma y. So z is equal to a function of x, y. So the independent variables are down here and the dependent variable is z. Okay, and let's say this function looks something like this. Let's say it was a kind of a weird looking top hat or something like this, and it had something like this, and so I'm trying to draw a three-dimensional looking thing. So you can sort of see there's bumps and everything in it. It's not very symmetrical, definitely, but this is a three-dimensional object. I mean, you can sort of see that by looking at it. It's got depth to it and length and height, and it's like a top hat, but it's got these crinkles in it, and I would like to calculate the volume of that thing, okay? Well, what if I wanted to project this down on the xy plane and just show you the big picture here, okay? What if I project this down here, okay? Then this function that's hovering, so to speak, over the xy plane is going to have some sort of projection down here, okay? Literally, if you shine a flashlight on top, it's going to project something down here. So let me do some labeling here and try to tell you where we're going with this, okay? This function is a function of x and y. That defines the top here, okay? This part down here, the projection on the xy plane is very important. It's called the region R. This region R, I'm going to refer to it through the entire lecture. So the region R is always the projection of the function down on the xy plane, okay? And then this body here in the center, from the top of the top hat all the way to the projection on the xy plane, this is called the volume D. The volume D. So to rephrase the question maybe a little bit more clearly, what if I had an object that looked like this? It had this irregular boundary down here, it was straight up like this, and it had this weird crinkly top hat looking thing, and this whole thing formed a volume D. The volume is everything from here all the way up and including all the way up to the top of the top hat. That's the volume. It's definitely not symmetrical, so I can't use this nice relation. Okay, my question to you is, how would I actually calculate this volume? What would I do to calculate that volume? Okay, what would I do? Well, what you can do is you can chop this thing, okay, up into a ton of little skyscrapers. And if you know the volume of each individual skyscraper, you could add up all the volumes and you'd have the volume, or a pretty good representation of the volume of this whole thing. Okay, so I'm going to draw one such skyscraper, which is just going to be a square cross section going all the way down here, like this. Okay, and so this guy is going to have effectively something like this. Okay, I didn't quite draw my drawing exactly right, but I think you get the idea here. Okay, so this is it's a square little skyscraper that goes from the bottom all the way up to the top. Okay, now let me continue drawing some terms here. This guy right here is called delta A, which is just an area element. Okay, we'll see what this means in a second, okay? And what I'm talking about here is the height here. The height from where the skyscraper goes and kind of touches the top of the top hat here, okay? The height is F of x comma y, because that's where the function is. The f of x comma y is by definition the height above the xy plane at the center of delta a. Okay, so you can see what I'm doing is I'm setting up what I'm going to eventually show you how to calculate the volume of this whole thing. But what I'm doing in the meantime is I'm just sort of laying the foundation, okay? You've got this function, it hovers over the xy plane, it projects a shadow down there, okay? It creates a volume element as it goes down and touches the xy plane. I want to calculate that volume. So the first thing we do in calculus is we start chopping the problem up into a ton of infinitesimally small chunks, and that's what we've done here. So you can imagine a little square cross-section in the xy plane coming up and making a skyscraper and intersecting with the top here. And if I calculate the volume of this one little skyscraper, if I know how to do that, or an approximation of how to do that, then I can just add up the volume of all the little skyscrapers, which I'm going to give a little bit away here. You're going to add them all up by doing integration. That's exactly the way we do the integration in Calculus 1 to add up infinitesimal little area elements. Here we're going to add up an infinite number of little infinitesimally small volume elements, okay? So what we have there is that. And if we add all these things up, as the skyscraper moves around all over the place, and if you make them small enough, then you'll approximate this volume very well, and you'll calculate the volume of this region D, which is what we care about. Okay, so the volume then is just sort of in quick notation, is going to be the sum over K, and I'll explain this in a second, of delta A sub K. Remember, delta A is just an area element, one of these little area elements here, okay, times the function x comma y. Okay, so this is sort of shorthand notation. You're not going to use this in your homework problems. It's sort of laying the motivation here. Okay, what we're doing is we're taking the area element A, which is just an area here. If we multiply the area of this base here, which is just something we know to be very small, but there as a square little area element. If we multiply it by the height, which is, by the way, f of x comma y, the function that we care about, if we do this multiplication, area times length is going to give me volume. So that this guy right here is the volume of this little skyscraper. I have no idea how to calculate it, but that's what it is. And if I sum over k, where if I have an infinite number of these little skyscrapers, and if I sum over them, then what I'm going to do is I'm going to approximate the volume of the whole thing. So that's really what you're doing, okay? So if you do two things, just like this is where the arm waving comes in a little bit, and you can look in your calculus book and get more of a warm fuzzy feeling. But if you shrink the area down to 0, at the same time that you add up the infinite number of skyscrapers that you have, you will arrive at the volume of this region that you have here, okay? And when you do that, this summation, because you see you're moving the skyscraper along x because you're moving it over here, and you're also moving it along y in order to capture the whole volume here. So you're really moving the skyscraper in two directions to add everything up, right? So what you're doing is, when you do this business, is the volume, the magic of calculus, makes it the double integral over the region R, and we'll talk about this in a second, of the function that you care about, over the element d sub a, or dA, which is the area element, okay? And that is exactly what the definition of the double integral is, okay? So when you see a double integral, you always need to know what you're looking at. You're integrating a function, just like you always have been. It's just now it's a function of two variables, x and y, okay, instead of a function of x. And because you have a function of two variables, you can't just integrate in one direction. You have to integrate in two directions because you have two variables. Okay, and so that's what we're doing here. And so we say in shorthand notation, this is just shorthand, that we're integrating over the region R, which is this whole region, this whole projection along the xy plane. Basically, we're integrating the function, but we're integrating it over its projection in the xy plane because that is the extent of the function. Just like when you're integrating in regular calculus, some function between 0 and 4. Well, you just say, well, I'm only interested in 0 and 4, and I'm going to integrate between those points. When I integrate this function, I have to define the region over the xy plane that I care about integrating over, and that region is called R. Okay? Now, I haven't told you really how to set this up practically yet, but intuitively, that's what it is. You're integrating over this fuzzy boundary down here, and you're adding up basically the volume elements as you go. That's what you're doing by the integration here, and you're integrating over dA, which is the little volume element down here, and you're moving that around, okay? So that is conceptually what you're doing. Conceptually and practically, aren't the same thing, okay? You'll see this in your book, and that's why I'm presenting it here for you. I think it's really important and really good for you to know conceptually what you're doing, but in real life, you're not going to have dAs running around in your integrals. You're not going to have region Rs running around your integrals. You're going to have X's and Y's. You're going to have real life integration along X and Y, but fundamentally what you're doing is you're integrating over that region dA, that region, that area region down there, because that's the extent of the function you care about. So in order to practically set up the integrals in your homework and show you how to do that, I need to present a couple of more quick things that are very important to do that, and then once we do that, we'll jump into the problems and get there. And if you're not quite sure, you know, you may be tempted to rewind and watch this right now and see if you can catch it a little bit more. I'd recommend that you just continue watching and get through the first couple of problems and then rewind if you want to, because this isn't going to be totally solidified until we work a couple of problems, and this certainly is not going to be crystal clear until we get to that point, but I hope it's a good introduction. Okay, so in order to do the problems, I need to present a couple of things. I need to present, it's all going to be dealing with the region R that we were talking about before, okay? If the region R, okay, looks something like this. If I have, looking down on the X, Y plane, okay, here's a three-dimensional view of what's going on here, but now I'm asking you to look down on the XY plane, okay? If what you're looking at, and don't worry so much about why I'm telling you this yet, just grin and bear it, okay? If you have two functions like this is g sub 2 and this is g sub 1, this is called vertically simple. I know you're probably thinking, why is he telling me this? This has nothing to do with what we talked about. Just understand what this means, and then you'll use it and learn it here in just a few minutes, okay? You have two functions like this that are, they're not really parallel, but they're roughly parallel. They don't intersect like this, such that you can draw a line vertically and intersect this function once and then intersect this function once. That's called vertically simple, okay? If you have something that would look like this, it'll actually be called horizontally simple, and you'll see why it's important in a second. If you had something that looked like this, maybe a function that looked like this, and a function that looked like this one would be called, let's say, h sub 1, and this would be called h sub 2, okay? This one is called horizontally simple, because I can draw a line horizontally and intersect this one time and this one time, and it's horizontally simple. I can't really intersect it vertically one time because you see I'm cutting through this thing more than once. So you can sort of see by analogy, this is vertically simple, this is horizontally simple. And just to sort of beat it to death, if you had something, it was like a circle, let's say you conjoined and sort of affix these things together. Let's say you had something like this, and let's say this segment of the function up here was g sub 2. This section over here was h sub 2. This section over here was g sub 1. This section is h sub 1. This is simply called a simple region. Okay? Because it's vertically simple through here and it's horizontally simple through there, so the whole thing is called simple. It's not only vertically, it's not only horizontally, it's both, because you can do this like that, okay? Now, what if you had a crazy function or a crazy couple of functions that look like a rainbow? Here's one and here's the other, okay? This is vertically simple. I'm just giving you some examples so you can sort of see this is vertically simple because I can do this and I can only intersect the guys one time. If I start going this way, I start to intersect the functions more than once, so it's not horizontally simple. The final one, and then I promise we'll get to the actual double integrals here, and you'll see why it's important, is if you had a function like this, let's say it's h sub 1, and another one over here, and that's h sub 2, this is neither. It's neither horizontal or vertically simple. It's not simple at all. If you go this direction, you intersect the function more than one time, and if you go this way, you intersect the same function more than one time. So that is sort of a primer on vertically and horizontally simple regions. Really, the only reason it's important is because, I'll give you a little prelude, when you're doing your double integrals and you're integrating over the region R, This boundary, or the boundaries that you actually integrate over, are going to be defined by functions. And it's going to matter how you set your integrals up if this region is vertically simple or horizontally simple. That's really all that matters. And it's going to depend on that as to how you set your integrals up. So I need to give you a little primer on that, okay? So let's go ahead and move on. Just try to soak this up and see if you can sort of figure out what's going on there. And then when we get to the actual double integral representation, I'll bring it up to the forefront and tell you why I even told you this to begin with. Okay, now that we've given sort of the general overview of what we're doing as far as what we're motivating ourselves to accomplish with double integrals, and now that we've introduced the concept of what a vertically simple and a horizontally simple region is when you have two functions that are sort of sitting there next to each other, and how to tell if it's vertically or horizontally simple, let's go ahead and write down the relations for how to actually use a double integral, and then let's blow right into solving some problems. And what you'll see is that the actual integration is not that big of a deal. You just have to take it one step at a time, okay? So what we will do is the following. If the region R, which is the same region in the xy plane that we had just talked about that was so important, is vertically simple, between the graphs of G1 and G2, okay? And what I mean by that is we're looking down on the x, y plane, we're looking down, okay? So here's a function here, and here's a function here, and this is G1, and this is G2. This is vertically simple because I can cut through each function only one time, okay? Now what I'm doing is what I'm going to end up doing is I'm going to end up using these functions to form my region R that I'm integrating over, okay? So if the region R is vertically simple, then you write the double integral as follows, okay? The double integral over the region R of f x comma y dA, this is just what I wrote down on the previous board. I'm integrating the function over the area element over the region R in the xy plane, which is the projection of that thing in the xy plane, is going to equal the integral, okay? Let me just write it down, a to b. Then I'm going to have here f of x comma y dy dx, okay? And this is going to be y is equal to G1 of x, and this is going to be y is equal to G2 of x, okay? So soak that in and just let it burn in your head, and you'll see what we're doing here, okay? I want to integrate this function, which is a function of two variables, and I'm going to integrate it over an area region dA. Now in real life, because I'm in rectangular coordinates, when I'm looking down on the xy plane and I'm trying to find out what region am I going to integrate over, I'm not going to be using dAs because I have an xy coordinate system. So I'm going to bound what I'm going to integrate over in terms of y and in terms of x because I'm using a rectangular system right now, okay? So if you can visualize this, in this case I'm looking down at the xy plane, so my actual function is hovering over this right here. This is my hand. It's sort of a three-dimensional thing that's sort of sitting here, and I'm integrating this thing over this region R, okay? So what I'm going to do is, let's say that I want to choose my region R that I care about, that I want to integrate over. Let's say I want it to be between this dotted line and this dotted line. And this dotted line was at x is equal to 1, and this dotted line was x is equal to 2. Okay? So you see, by using a function g here, which is a y equals a function of x, which is this function right here, and another function below it, and two fixed values of x, 1, and 2, I can define, I should say, a region here. This region is the region R. Okay, that's the region I want to integrate over. So what I'm trying to get at is, in order to define the region R, you have to use two functions, okay? And when it's vertically simple, you organize your integral like this, okay? First thing you do is you take your function, you integrate it over y, okay? You integrate it along y, which is integrating along this direction right here, okay? And you're integrating between the values of y is equal to whoops, I did something a little bit kooky here. This should be G1 and this should be G2. So you're integrating from G1 of x to G2 of x. So what you're doing is you're integrating from this point up to this point, but from this graph up to this one, and you're integrating your function over this point, okay? And a to b is just integrating along x right here, okay? So by using the combination of 2, I'm sweeping out an area that I'm integrating over, and that area is the region R. Let me say that one more time. It's absolutely crucial that you understand this, okay? We're integrating some function that's hovering over the xy plane. I need to integrate it over a two-dimensional sort of surface area, which is a region R, okay? The way we do that is we have to have, we integrate from one function up to another, and then we integrate from one value of x to another, okay? So if we start here, if I were to integrate along this line right here, then I would get some contribution right here from this function to this function right along here, and then I would move over and do it again, and I'd move over and I'd integrate again, and I'd move over and I'd integrate again and again and again. The whole time I'm sweeping out an area here. The way you mathematically do that is you take your function, you integrate along y, but you have to know what limits to put in for y, okay? But you can't just put numbers in here, okay? Because you're sweeping, you know, in a regular shaped area down there. So what you do is you define a function g sub 1 that's going to be the lower boundary, and another function g sub 2 that's going to be the upper boundary. You integrate y along y between those two functions. The reason is because y is equal to g1 of x and y is equal to g2 of x, okay? So you're integrating along y, okay? You're going to have some functions here, and then after you do that, you're going to integrate from 1 to 2, or from a to b. In this case, I've drawn it as 1 to 2. But whatever limit you choose from x to y. The combination of the two, the combination of these two functions and these two numbers, define what the region R is. Okay? So I think I've said it enough times. Let me go ahead and write down the corresponding relation for the horizontally simple region, and then we'll just solve some problems, and you'll start to see how the pieces of the puzzle fit together. Okay? So if the region R is horizontally simple between graphs h sub 1 and h sub 2, then it's going to be a very similar story. And you're not going to use this representation very much, but I'm putting it here for completeness. The integral over R of f sub x comma y over the area dA, I'm integrating a function over some region R, okay, is going to be some integral, just let me get it all down on paper, h1 of y, h2 of y, okay, and I'm integrating the function f of x comma y. Now I'm going to integrate dx and then dy, okay? So you can see it looks very similar to what I have before, okay, except now the region, if it's horizontally simple, the region might look like this. I might have an h1 and an h2, okay? And these are the two functions, and it's horizontally simple, and let's just say for whatever reason that it's organized that way, and I want to integrate that direction, okay? So now, instead of integrating dy and then dx, I'm going to integrate dx and dy. This is x, this is y, okay? So don't forget that when I have functions of y, what you're saying implicitly is x is equal to that function, and x is equal to this function. So I'm integrating along x right here, okay? So I would integrate along x here, and then I would continue integrating and sweeping down to my final destination down here, and as I do that, I'm sweeping out an area in between everything here, and this is called the region R. Okay, so I'm integrating over the region R. So I'm doing exactly what I'm doing before, it's just that instead of having my functions organized like this on top of one another like this, the functions are organized side by side, and that just depends on the problem. The problem might tell you, integrate the function yada yada, okay, between the two equations given by this, and they may give you equations that look like that, okay? So you're going to have to organize the integral appropriately. In that case, you'll integrate along x first. The most confusing thing about the whole thing is you would think that when you're integrating along x, you wouldn't have a function of y here and here, okay? You would have x's here and here because after all, you're integrating along x. What you need to remember is that when you're integrating along x is equal to a function of y in this case. You know, when you have equations that are tilted on their side like this, x sort of behaves, x is the the independent variable, so to speak, and y is the dependent variable. So everything looks a little bit backwards. So you're going to have function of y here, function of y here. You're integrating from this function up to this function, okay? And then c to d is just integrating whatever boundary you might have here. So this might be c, and this might be d, integrating there. So again, between the functions here and the numbers here, you've defined a region R. So in all cases, you're going to be integrating, and you're going to have some functions in one of the integrals and some numbers as limits of the others. And in this case, you're just switching the order here, okay? Now, fundamentally what you're doing is you're integrating the function, and you're plugging in, you're doing one integral first. This integral would be the one you would do first. You get the result of that, you take the answer you get, and you integrate again with respect to the other variable, okay? The only other thing I really need to say is that when you integrate a function with respect to y, you do the same thing you do with the partial derivatives. When you integrate a function with respect to y, you hold all of the x's exactly as if they're constants. The same rule that you use for the partial derivatives, okay? And then if you're integrating along x, you hold all of the y's constant. So that's the fundamental thing. And I think now at this point what we need to do is just go ahead and work some problems and get some experience for what this looks like. It looks like Greek here, but I think that once we work some problems, it'll solidify itself and become a little bit more familiar to you, okay? So let's do that. If you were just given the double integral as follows: 0 to 1, negative 1 to 1, the function is x, and I'm integrating dy dx, okay? Now, mathematically, okay, what you have here is you have an integral here along y. So you integrate this function holding holding x constant, because everything other than what you have here, the dy, everything other than y is a constant. So you do that integration, you plug in the limits, and then you take the result and you integrate along dx, and that would be holding all of the everything other than x constant, okay? And we're going to do that, and you could certainly do that without drawing any pictures at all, but I really want to drill in what this region looks like to you so you can sort of get an idea here. What does this region look like that I'm actually integrating over, okay? This is x, this is y, I'm looking down. This is a function that's hovering over the xy plane, so to speak, okay? And I'm integrating from y is equal to negative 1 to y is equal to 1. Those aren't just values, those are numbers, okay? So this is y is equal to 1. This is y is equal to negative 1, okay? And because they're just constants, this is just a line that goes like this, and this is just a line that goes like this. So this is the two functions, okay, that are bounding my, my region exactly in the same way that these two functions are drawn over here. It's just that this function is a very simple function, it's a constant, okay? And also I'm integrating from x is equal to 0, which is right here, right there, on up to x is equal to 1, which, let's say, just for grins, is right here. So x is equal to 1. Okay? So if I kind of enclose this like this, because it only goes this far, this guy right here is a region R. And that is what I'm integrating over, okay? I'm integrating from y is equal to negative 1 up to positive 1, and I'm integrating that function like this, and then I take the result and I integrate from x is equal to 0 to x is equal to 1, okay? And these are numbers in this case, but the thing you have to remember is when you have the first integral that you do is always going to be basically a function in the limits. So this is really a function. I mean, it's a constant number, right? But you know that y is equal to 1 is a function that's just sort of a flat line right here. So that's why it looks like that. In general, way back over here, we said that here is going to be, y is going to be a function of x up to another function of x. And yes, it is a function of x, it just happens to be a constant, okay? So that's the region of R that we're doing here, and we're integrating this function over this region of R, okay? So let's go ahead and do it. Okay, so what we're going to have is, first, let's work on this inner integral. I'm not going to worry about this integral at all. I'm only going to work on this one. The integral of x with respect to y. This means that anything other than y is now a constant. This x, for all practical purposes, is a constant. It could be 2, it could be 19, it could be negative 4. It's a constant. So if this is a number and I'm integrating, this is going to be a constant. It's just going to hang along for the ride, and then I'm going to have a y here. okay, because I'm integrating along y. Imagine if you were integrating 2 dy. I said take that integral. Well, you would say, okay, well this 2 comes here, and then there's nothing here, so y hangs over, and that's the answer to the integral, okay? That's your integration 101. I'm not going to go into details of why that's the case. You guys know this already. So if x is a constant, it hangs along, and there's no y here, so when you integrate, a y pops up. That's just your basic rule from Calculus 1, okay? So the answer to this little integral here, which is kind of like a partial integration because you're only integrating along y, is xy, and you're evaluating from -1 to 1. But don't forget, and this is also equally important, when you do the evaluation, you integrate it along y. So here, when you evaluate, you're only plugging in for values of y. So what you're going to have is, you're going to have x times y evaluated here minus x times y evaluated here. You evaluate the top point minus evaluating at the bottom point, but when you plug it in, you're only plugging into the y because that's what you integrated along in the first place. X is a constant in this relation, okay? So what you're going to have here is x plus x, which is 2x. So the answer to this integral here, when you evaluate it, comes out to be 2x, okay? Now, the result is now plugged into another integral like this, because the original integral had dx out here, and we're going from 0 to 1, we have to integrate this, okay? This is just a straight, regular old integral from Calculus 1, 2 over 2, exponent plus 1, exponent squared, evaluated from 0 to 1, okay? So this is just going to be x squared evaluated from 0 to 1, okay? And then what we're going to have here is we're going to have 1 squared minus 0 squared, evaluating the limits of integration, which is going to be equal to a big fat 1. That's the answer, okay? So congratulations, you've done your first double integral. You can see mathematically it's not so bad. I mean, you just start with the inner integral, you integrate this guy along y, so everything other than y is a constant. Any other variable is a constant. So you treat it as a constant. It comes along for the ride. The y comes up because that's how you're integrating here. It's just a regular rule of integration. You evaluate the limits, but when you plug in the limits, you only plug into y because that was what I integrated along, okay? You get the result, and then you integrate again according to the outer integral. So now first you integrated from here to here, and now you're integrating from here to here. The combination of the two allows you to integrate over a surface area, okay, region R, and that's what we talked about way early on. So we just did this integral exactly as you do any basic elementary integral, and the answer you get is the answer for that double integral. Okay, let's continue on and do some more integrals, and we're going to slowly crank up the complexity. And what we're going to do is we're going to methodically build our skills to do these double integrals, okay? So that is your integral. You have a function of 2 variables, okay? And you're integrating over a region R that's defined by this information up here. Now, if you wanted to figure out what that actually looked like, and in the beginning I do actually very much recommend that you do that, this is the xy plane. You're looking down on the xy plane. Your function, which is right here, is hovering over the xy plane. Okay, it's a 3-dimensional sort of construct, and you have defined, with the limits of integration here, you've defined some region R in the xy plane that you plan to integrate over, okay? And so let's figure out what that looks like. You're integrating along y first from 0 to 1. So this is y is equal to 0. That function is just a horizontal line. Y is equal to 1 is another horizontal line, which goes like this. And then along x, you're integrating from the point 0 up to the point 1. So this is your region R. Okay? You're going from y is equal to 0, which is a function that's a horizontal line, up to y is equal to 1, and then x is equal to 0 to x is equal to 1. So you're just evaluating over that region R. You're evaluating this integral over this region R. You're evaluating this function and integrating it and adding up all those little skyscrapers, etc., over the region R. Okay, so what do we do next? I literally do this on my paper. I'm going to work on this integral first, which is going to be the integral of 0 to 1, e to the x plus y dy. I'm only integrating along y, okay? Now, I don't like having an x plus y up in the top because, you know, what I've said here is because I'm integrating along y, x is a constant. Okay, I'm integrating in this direction first, so x is a constant. It doesn't matter. So this could be 2 plus y or 3 plus y or whatever, but I don't really know, maybe you guys do, but I don't really know off the top of my head what that looks like. Okay, so what I'm going to do is I'm going to do a quick substitution. U is equal to x plus y because I want to get this function in terms of e to the u, something I know how to integrate. Okay, du with respect to y, because that's what I'm integrating with respect to, is just going to equal 1, right? Because if I take the derivative with respect to y, then I'm holding x constant, and so the derivative is going to be 1. So du is equal to dy. Now, why did I do all of this? Because I'm going to rewrite this integral, okay, as the integral from 0 to 1 of e to the u now, because I've defined it like this, dy, but dy is equal to du, okay? dy is equal to du. So that's going to be equal to e to the u, that's the integration, evaluated from 0 to 1, but I don't want to do this evaluation yet because I've got my variable of substitution tied up and I've got a different limits of integration, which is in terms of y. So let's go ahead and substitute back in e to the x plus y evaluated from 0 to 1. Now, if you know how to integrate this without doing this, that's fine. I just like to do it myself because I like to see how my exponentials are before I actually do the integration. Now, when I plug in the limits of integration here, I'm only plugging in for the variable y because that's what I integrated across. So plugging in for the top, it's going to be e to the x plus 1 minus e to the x plus 0, so to speak. So basically what I'm going to have here is e to the x plus 1 minus e to the x. That is going to be the value of the first integral here in the middle. And then now I'm going to take that result that I just got and I'm going to integrate along dx. Okay, so taking this and continuing on, I'm going to have the integral from 0 to 1 because of this 0 to 1, and I'm going to integrate the result, which was e to the x plus 1 minus e to the x along now dx. So I've already done my integration along y, now I'm doing my integration along x. Now it becomes a regular old integral. It becomes a regular integration, and now that I've done an integral of this form, I know that this integral of e to the x plus 1 is simply e to the x plus 1. That's the answer to that integral. And the integral here is just e to the x, and I can evaluate it from 0 to 1. So I just integrated both of them, okay? And when I plug in for the top, I'm going to have e to the 1 plus 1 minus e to the 1 minus e to the 0 plus 1 minus e to the 0, okay? So here I'm going to have e squared minus e, and then here I'm going to have minus e plus 1. So I'm going to have e squared minus 2e plus 1. E squared minus 2e plus 1. That is the answer to the double integral. So I had a function of two variables. I defined a region in the xy plane given by the limits of integration here. I integrated along y first from this line here up to this line, and then I integrated along x from this line to this line. That defined a region R. I integrated over here. I just integrated the along dy first, holding x constant. I did this integral with a little bit of substitution. When I plugged in the limits of integration, I did it only by plugging into y because I was holding x constant the whole time. I took the result, integrated it again along dx, and then that's just a regular integral that falls out from your calculus 1, and that's how you get the answer to that. Okay, so you can see, you know, it's pretty systematic. You integrate the inside, then you integrate the outside. You just have to make sure you plug in your limits of integration appropriately. What if you were given the integral from 0 to 1, and then here's something a little bit different. Integral from x to x squared, okay, of 1, that's what I'm integrating, dy dx. Now, if you go back to the beginning of this lecture, you'll see that in general, the inside integral of a double integral is going to be a function. Here, it's x squared and x because y is equal to x, y is equal to x squared. Okay, so what you've done here is you've defined This is the xy plane. I'm only integrating the number 1, but effectively that's a function that's hovering over the xy plane. And then this information in the limits of integration define the region R that I'm talking about. Now, the function y is equal to x, looks something like this. Y is equal to x, okay? And the function y is equal to x squared looks something like this, okay, up there. And I'm integrating from x is equal to 0 to x is equal to 1. So effectively what you're doing is you've bounded this thing like that. So you're integrating over that region R. Now going back here, the reason these limits of integration were so beautiful here, just numbers, is because these were rectangular regions I was integrating over. So I was careful to tell you the whole time that when you're integrating from here to here, this is a line and this is a line. This is a number and this is a number. It formed a nice, beautiful, rectangular region, so the limits look great. Here, this region looks pretty wacky. You're integrating between this curve and this line, so you're integrating between a line here and a curve here, okay? And then these are functions because y is equal to x and y is equal to x squared. You're integrating along y. You're integrating this direction first, and then you integrate from 0 to 1, that direction. The combination of the two sweeps out an area. That is what you're integrating over. Now that we've got the formalities out of the way, let's actually do the integration. I'm going to integrate this guy. I'm integrating a number 1 along dy. So there really is nothing to hold constant. There's no variable there at all. So the answer to this integration, I think you'll convince yourself, is just y, just like a regular integral. But you're evaluating it from x to x squared. And you're going to plug these in to here as follows. You would have, plugging x squared in here, you'll have x squared minus, and plugging x into here, you'll have x. So this is the value of that inside integral there, and now I need to take that and integrate it along dx. So I'm going to take this, and I'm going to integrate it from 0 to 1, this 0 to 1, x squared minus x along dx. Okay? And this is a regular one-dimensional integral from Calculus 1. How do you integrate this? 1/3 x to the third minus, integrating this one, 1/2 x squared, evaluated from 0 to 1. X is equal to 0, x is equal to 1. And what you would get here, plugging in 1, you'd get 1/3 times 1 cubed minus 1/2 times 1 cubed minus, and inside this is going to be a big fat 0 because plugging in 0 into both of these places is just going to give me 0. So in the end I'm going to have 1/3 minus 1/2, okay, 1/3 minus 1/2, and then to simplify this fraction you can rewrite this as 2/6 minus 3/6, double check me here, 2/6 is 1/3, 3/6 is 1/2, I just found the common denominator here, so that would be negative 1/6. Negative 1/6. So again, you've got an inner integral here, and when you finish getting this and evaluating it, you should get a function of a function back that you could then plug in and integrate along x. Okay, you can integrate that along x very nicely, so that the only thing you have left at the end of the day is just a number. And what we've done is we've integrated from this function up to this function along y. These were functions, and we integrated along x from 0 to 1. This is vertically simple region because I can cut like this and only cross the function one time. Okay, let's continue on to another example. Integral from 0 to 2, integral from 0 to the square root of 4 minus y squared. Okay, the function I'm integrating is x, and I'm integrating along dx dy. Now notice here that this is different than the previous examples. Here, it's not dy and then dx, it's flipped backwards. So this is a horizontally simple region. This is an example of integrating over a horizontally simple region. So big picture, instead of, in the other examples, we integrated between some function here and some function here, between two numbers, generating our region. Here, we're basically integrating between two functions here, this one, and this is x and this is y. And that's why first we're integrating along x, we're integrating like this, then we integrate along y like this. But in either case, we're generating or we're integrating over an area A, and that's why it's useful. Okay. So mathematically, though, if someone gives you a function like this, you really don't have to do too much thinking. I mean, you don't have to draw the region R every time. I mean, if they give you the integral with the limits appropriately there, all you have to do is actually do the integration. You don't have to draw the region out. I'm just trying to do that to help you out in visualizing this stuff. So the first thing we're going to do is we're going to look at that, and we're going to integrate this along x. It's pretty easy to do because it's a function of x. I'm integrating along x. So it's going to be 1/2 x squared. That's all it is. Evaluated from 0 to the square root of 4 minus y squared. Okay? 4 minus y squared. And actually doing that evaluation, I'm going to have 1/2 square root 4 minus y squared minus, plugging 0 into here, I'm going to have 0. So that's what I get there. And then over here, the square of the square root drops the square root away. So I'm going to have, on the top, I'm going to have 4 minus y squared over 2. That's what that's going to reduce to, because the square root goes away. And that's going to reduce to 4 divided by 2 gives me 2 minus 1/2 y squared. All I'm doing there is I'm taking these two and I'm dividing and I'm getting 2, and I'm taking these two and I'm dividing and I'm getting this. Okay, so what I'm going to do now is I'm going to take what I've arrived at here and I'm going to plug it back into this outside integral from 0 to 2. 2 minus 1/2 y squared dy. Okay? And I can evaluate that by integrating this first thing, which is going to be 2y, and evaluating the second thing as 1/2, which is the coefficient, over the exponent plus 1, which is 3, times y cubed, evaluated from 0 to 2. Okay, so it's just the first thing integrated here, so you're going to get 2y, and then this is just the coefficient over the exponent plus 1 times y to the exponent plus 1. So what I'm going to have here is 2y minus 1/6 y cubed evaluated from 0 to 2. It's 1/6 because this really is 3 over 1. I can take him and flip him over and multiply, so I'm going to have the 1/6 there. Okay. So in the end of the day, I'm going to have, plugging in for 2, I'm going to have 2 times 2 minus 2 cubed is going to be 8 over 6. 2 cubed is 8 over the 6 minus, I'm going to put y in both places. That's going to give me 0, so this is going to be a big fat 0 there. So I'm going to have 4 minus 8 over 6. Okay. Okay, so the first thing I'm going to do is I'm going to say 4 minus, simplifying this right here, is going to be 4/3. Okay, and then here I can find a common denominator by multiplying this 4 by 3 over 3. Okay, so multiplying the 4 by 3 over 3 changes nothing. Okay, because I'm multiplying by 1. What I'm going to get is I'm going to get 12 over 3 minus 4 over 3. So what I'm going to get at the end of the day is 8 over 3. And the answer is 8 over 3. So recapping this, I've got a very simple function that I'm integrating over some region in the xy plane. It's getting a little bit complicated to figure out what these regions look like, but basically this is a horizontally simple region because I'm integrating first along x and then along y. And that was given by a couple of boards ago when I showed you that flipping the order here and integrating along the other direction first is actually integrating along the horizontally simple rather than the vertically simple region. Okay, but in any case, mathematically it's the same deal. You integrate along x, so we got the 1/2 x squared. We plugged in the limits of integration, and we got this. We took this and we integrated this along the other direction, the y direction, which is just a simple integration from calculus 1. Get the 2y, get this guy, y to the third, and you just do your evaluation of the limits of integration, and you get a number. Okay, so it's up to this point we have done problems where you were given an integral. Integrate this. You have two integral signs, the limits of integration are given, and all you have to do is integrate it. You really don't have to draw the region unless you really want to visualize it, because if you're given everything, you can just bang through it and do it. You do the inside integral first, holding whatever constant that you need to, and then you do the outside integral. Okay, one goes into the other. Now the remaining few problems, what we're going to do is I'm going to tell you to integrate a function, but I'm going to not give you the limits of integration. I'm just going to tell you in a sentence form what the region R should look like. Okay, so I may tell you it needs to be between the graph of this and the graph of that. in the XY plane. And you need to go and figure out what the limits of integration are. This turns up the gain a little bit and makes it a little bit challenging in this section to figure out what to do, but it's really not that hard. You just have to internalize what you're doing, which is integrating, if it's vertically simple, integrating first along Y and then along X. You get that in your head and get it straight, then these will not be a big deal. So the question would look like this. Find the double integral over the region R, I have not told you what the region R is, of the function x plus y dA. Okay? Now that doesn't help you at all because you don't know what the limits of integration are at all. Okay? And then the problem would tell you R is the triangular region bounded by the lines y is equal to 2x, x is equal to 0, and y is equal to 4. Okay? So I've given you the function to be integrated, but I haven't given you the limits of integration. I've just told you roughly that the region R that you're integrating over is going to be bounded by these lines. So the number one thing to do when you're given a problem like this is to draw the region R and figure out what the region looks like and figure out what your limits of integration are. And then once you do that, you can just simply crank through the math. Okay? So we're going to do that now. Let's see if we can figure out what this region actually looks like. Okay, if this is x and this is y, okay, let's see if we can do a good job at figuring out what this is. X is equal to 0. What does that look like? Okay, well, x is equal to 0 is a line going up and down right here along the y-axis. So I'm going to kind of replace the y-axis with x is equal to 0. Okay, so that's the first boundary of this region. Okay, the next thing is y is equal to 4. So I'm going to have 1, 2, 3, 4. So this is going to be 4. And y is equal to 4 is a flat line that goes off like that. Okay, so now we're starting to bound some sort of area. Now what's the other remaining thing? Y is equal to 2x. We know it's a line. We know it goes through the point 0, 0, and the slope is 2. So if this is, let's say, x is equal to 1, x is equal to 2, then the slope is going up 2 for every over that it goes once. So 1, 2 over 1. So it goes through this point here, and it might look something like this. Okay, I drew that in a bad way. It needs to go basically through this point here. So you see it goes up 2 over 1, up 2 over 1. That's because the slope is equal to 2. This is y is equal to 2x. This is y is equal to 4. So we've got all three pieces of information here, and so the region R that's bounded is this triangular region right there. So you see, here's the xy plane, we're looking down on it. The function that we're integrating hovers over this region like this, and what we're doing now is we're integrating over this triangular region. Okay, so now that we know what we're doing, let's go ahead and try to fill in the limits of integration, see how far we can get. We know it's going to be the double integral, we know it's going to be x plus y, and now that we know that this is it can be a vertically simple region like this, we're going to write it as dy dx. We could, if we really wanted to, integrate it as a horizontally simple region, but for all practical purposes, doing the vertically region is a little bit easier to think about, at least for me, and you get the same answer both ways, so we're going to do it that way. So we have our dy and dx. What would we put for the limits of integration along y? Well, we know we're integrating from this function up to this function here. So this is y is equal to 2x up to y is equal to 4. So we're integrating between these two lines in the y direction. So y is equal to 2x up to y is equal to 4. This is a line and this is a line. Okay, so that's what I'm putting for the limits of integration along this direction. Now, what do I put for the limits this direction? Well, I know I'm going from x is equal to 0, so I'm going to put that all the way up to this point. Okay, and you can look at the graph and figure out that that's x is equal to 2. So you can put that right there. If you didn't know, or if you didn't graph it, you could easily find the intersection of these two lines, because y is equal to 4, which is also equal to 2x. So x is equal to 4 divided by 2, which is 2. So x is equal to 2. That's the point at which those two lines intersect. So here is where you would have arrived if they just gave you the problem in the book and said integrate it. But in this case, they gave you the lines that bounded the region R that we cared about, and you had to figure this out. You had to figure out from what limit up to what limit in y and also in x. But the good news is that once you're done with that, the problem is really half solved. All you have to do is integrate. Okay, so now we're integrating along y, so that means I'm holding x constant. X is a constant here, okay? So it's just like a number. So I integrate this, I'm going to get x, y. Just as if this were 2, it would be 2y, okay? Plus, now I'm integrating y, it's going to be 1/2 y squared, okay? And I'm going to integrate that from 2x up to 4. Okay, so what I'm going to have here is I'm going to have plugging in here, plugging into y, by the way, because I integrated along y, so when I evaluate the limits of integration, I'm only going to plug into the y's. So I'm going to have x times y is equal to 4 plus 1/2, 4 squared is 16. I'm going to put 16 right there. Okay, and then I'm going to subtract off plugging in at 2x. Here I've got x times going into y, 2x. Okay. And here I'm going to have plus, I'm going to go ahead and get rid of this for now. I'm going to have plus 1/2, and I'm going to have 2x going into here, which is going to be 2x squared. Okay, 2x squared. Okay, so let's go ahead and do some simplification, beat this into shape. I'm going to have 4x plus 16 divided by 2 is 8. Okay, and then over here I'm going to have minus 2x squared. And then over here, I'm going to have 4x squared, but I'm dividing by 2, so it's going to be, with a negative sign here, I've got 4x squared divided by 2 is 2x squared, and the negative sign comes from out front here, okay? And so at the end of the day, I'm going to have, this guy here is going to be negative 4x squared plus 4x plus 8. Okay, that was the answer to the inner integral here after I did the evaluation. Now what I'm going to do is I'm going to take this answer and I'm going to plug it in to the outside integral here, which is integral from 0 to 2 of what I had here. Negative 4x squared plus 4x plus 8 dx from this dx here. Okay, and now it's just a simple matter of doing regular old integration, right? So here I have negative 4 over 3x cubed, because it's this over the exponent plus 1, like this, plus 4 over 2x squared plus 8x, evaluated from 0 to 2. Okay? Let me just go ahead and do one quick simplification here. 4/3 x cubed plus 2. 4 over 2 is 2x squared plus 8x, evaluated from 0 to 2. Now, what I'm going to have here, plugging in for 2, negative 4/3 times 2 cubed is going to be 8, okay, plus 2 times, okay, 2 squared here is going to be 4, plus 8 times 2 is going to give me 16, minus, evaluating all this stuff at x is equal to 0 is going to contribute nothing because it's going to just give me a big fat 0 like this, okay? So what I have here is 8 times 4 is 32, negative 32 over 3, okay? Plus 2 times 4 is 8, plus 16, okay? So this is going to be negative 32 over 3, negative 32 over 3 plus 24, just adding the 8 and the 16. And then all you have to do here is get a common denominator. The easiest way to do that is multiply 24 by 3 over 3, right? So I can take this 24 and I can effectively multiply by 3 over 3, and that will give me a common denominator. So I'm going to have negative 32 over 3 plus, and 24 times 3 turns out to be 72 over 3. And when you actually do this subtraction, you'll have 40 over 3, and that is the answer. So let's go back up and review the bidding from the top. We were given a function to integrate over some region R, but I wasn't given the limits of integration. I was just given a few lines and said, figure out what the region is yourself. So we knew that it was between x equals 0 y is equal to 2x, and y is equal to 4, and it forms this triangular region, okay? So we went and we looked, and we did it as a vertically simple region, integrating along y first, and then along x, that direction. And based on the way it looks, you're going from this function up to this function. So it's 2x up to 4, and then going this direction, it's 0 going over to 2 where the lines intersect, okay? We did the inside integral holding x equal constant because we're integrating only along y. We got this stuff, and we plugged in the limits of integration, and we got this expression here. We took that, and we integrated that along dx with these limits, okay, going along dx, and this just turns out to be a regular old algebraic integral that you did back in Calculus 1. You get an answer of 40 over 3 as the answer to that double integral. Okay, the next problem is going to be similar. We're going to integrate over some region R the function 3x minus 5 over, the region dA, which I don't know what that is yet. And the problem tells me that the region R is the triangular region bounded by the following. Y is equal to x plus 5, y is equal to negative x plus 7, and x is equal to 10. Okay, so the first thing, just like before, is you need to figure out what your limits of integration are here on the double integral. The only way you're going to do that is figure out what the region R is in the xy plane that they're talking about here. Okay, so that's what we're going to do. And what I'm going to do is I'm going to say, well, this is the xy system, x, y, right? You're looking down on it. Your function here is hovering over it, and you're integrating that over some region R. That's what we have to figure out. Okay, now we know already that x is equal to 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. This is a vertical line down. X is equal to 10. This is one of the boundaries given by this. I've got two lines that I have to draw. Okay, so let's go ahead and first draw the first one, x plus 5. So the y-intercept is 5. 1, 2, 3, 4, 5. That's the, that's the y-intercept. I think I said the wrong thing. The slope is 1, so it means it goes up 1 and over 1. Up 1, over 1. Okay, so if I wanted to draw this one, this would look something like this, right? So this is going to intersect kind of up like this, okay? Y-intercept of 5, slope of positive 1, okay? Now what does the other one look like? Y-intercept of 7, so that's 5, 6, 7. So the y-intercept is here, but the slope is negative, okay? The slope is negative. That means I go down 1 and over 1. So down 1 over 1, down 1 over 1. So that means this one goes something like this, okay? So this right here is x is equal to 10. This one is y is equal to negative x plus 7. And this one is y is equal to x plus 5. And inside, you can see quite plainly that this is a triangular region that we're talking about here, okay? Now, it's a vertically simple region, so I'm going to go ahead and use that. And so I need to figure out what boundaries I'm going to use. I'm going to integrate along y first, so I'm going to integrate between this function, this line, and this line. Okay, and then I'm going to go this direction. Okay, so what I'm going to have is a double integral of the function 3x minus 5. I'm integrating along y first and then along x. Okay, now I'm integrating along y, so I'm integrating from this line up to this line. So I'm going to integrate from y is equal to negative x plus 7 down here up to y is equal to x plus 5 up at the top here. Okay, so that takes care of doing the integration along y. Now what about along x? You see this guy intersects here. I know I'm going to end up over here at x is equal to 10, so I can integrate up to 10. But what about this point? Okay, now I've graphed it, so it kind of looks like I can read it off the graph. But what I need to do is find out this intersection point, and that'll be because I'm integrating along this area that's bounded by this region, so I've got to know what that point is here. So how do I find that? The intersection of these two lines is what I need to do. Y is equal to x plus 5, that's that line, is equal to y is equal to negative x plus 7. So that's equal to each other. Let's move the x over here. So I'm going to have 2x. Move the 5 over here is going to be 2, so x is equal to 1. So this is x is equal to 1, and that looks like exactly what I drew on the graph. Okay? So it's going to go up from 1 to 10. So big picture, I'm integrating from this function up to this function, and I'm integrating from 1 to 10, sweeping out this triangular area here. Okay, now that we have this, let's go ahead and do the integration. Integrating this, let's integrate this along y. Okay, that means we're going to hold x constant. So everything in here is a constant. Okay, everything in there is a constant. Okay, so what I'm going to have here is, integrating this is going to be 3xy minus 5y. This is a constant, so y comes out there, and this is a constant, y comes out there. It's exactly as if you would integrate this, and this entire thing was a number along y, you'd have to put that in front of the y. Okay, that's just from your calculus 1, integrating a polynomial. Okay, you're going to evaluate this from negative x plus 7 up to x plus 5. And we're plugging this into the values of y because we integrated only along y. Okay, so this is going to equal, okay, 3x, and plugging into y, I'm going to have x plus 5. Okay, and then here I'm going to have minus 5y, and I'm going to plug this guy in here, x plus 5. So this is evaluating the top limit of integration. Now let me subtract off the bottom limit of integration, okay, which is going to be 3x, plugging in for this is going to be negative x plus 7, minus 5, plugging in here is negative x plus 7. Okay, so that's what I have here. I just need to simplify all that stuff in order to figure out the answer. So here, distributing in, I have 3x squared plus 3 times 5 is 15x. And then over here I have negative 5x minus 5 times 5 is 25. Okay, I'm going to go ahead and get rid of this because we don't need it anymore. Okay, and then continuing on down here, I'm going to keep things very explicit because I don't want to mess up a sign error. So I'm going to keep everything in a bracket here. 3x times negative x gives me negative 3x squared. 3x times 7 gives me plus 21 x right here, and then over here I'm going to have plus negative 5x times, negative 5 times negative x gives me 5, positive 5x, and then this times this gives me negative 7 times 5 is negative 35. Okay, so I kept it like that because I didn't want to screw myself up with signs trying to distribute this sign in on top of doing all of this other work. So I'm going to clean up a little bit of this. 3x squared 15x minus 5x gives me plus 10x minus the 25. Now I'm just going to simply, I'm going to keep this here for right now, and I'm going to clean everything up on the inside. Okay, now inside of this bracket here, I'm going to have negative 3x squared. 21 plus 5 is 26x minus 35. Now the only thing I'm going to do is distribute this negative sign, and I'm doing this one step at a time because I know from experience that trying to distribute too many negative signs in at once is just going to lead to confusion and get you the wrong answer. So that's plus 3x squared minus 26x plus 35. Now let's go ahead and collect like terms. 3x squared plus 3x squared is 6x squared. And I'm going to put a dot over this and a dot over this just to show myself that I actually added that stuff together. Now the 10x plus the 26x, or the minus the 26x there, is going to negative 16x. Okay, and I'm going to put a dot over this and a dot over this so I've reminded myself there. And then here, negative 25 and 35 is going to give me plus 10. Okay, so finally, 6x squared minus 16x plus 10. This is the solution to this inner integral right here, the one here. Now what I need to do is take that and integrate this along this outer integral here. So I'm going to do that next. So I'm going to take this and do it like this. Integral from 1 to 10 of what I've just received here, 6x squared minus 16x plus 10 dx. This is a regular polynomial integral, nothing fancy about that. So I have this 6 over 3 x cubed minus 16 over 2x squared, exponent plus 1, plus 10x evaluated from 1 to 10. Okay, from 1 to 10. So just before I actually do the math, 6 divided by 3 is going to be 2x cubed minus 16 divided by 2 is going to be 8x squared plus 10x evaluated from 1 to 10. Okay, and then what I'm going to have here is, evaluating at 10, I'm going to have 2 times 10 cubed. What is 10 cubed going to come out to be? 10 cubed is going to be 1,000. So I'm going to have 1,000 right here minus 8, okay? And what I'm going to have 10 squared here, that's going to be 100, plus 10 times 10 is going to give me 100, okay? And that's evaluated at 10, okay? And I'm going to subtract off evaluating everything at 1, so I'm going to have 2. Obviously this is 1, so it just drops away, minus 8, and then plus the 10 because I'm evaluating at 1. Okay, so what I have down here is 2 times 1,000, which is 2,000. Okay, minus 800. Okay, plus 100. And then over here, minus 2 plus 8 minus 10. And when you do all of this, 2,000 minus 800 plus 100 and all this stuff, you're going to end up with 1,296, which is the final answer. Okay, so let's review where we were at. We were told to integrate this problem, which is a function, and you can visualize it sitting over, this function sort of sitting over the xy plane. We were told to integrate it only along this triangular region. Okay, the region was bounded by the line x is equal to 10 and these other two lines that crisscross like this. Okay, we found the intersection point by setting the equations equal, and what we did is we knew it was vertically simple, so we set our integral up as a vertically simple integral, dy first and then dx. Okay, so integrating along y, this direction, we integrated from this line up to this line, y is equal to negative x plus 7 up to y is equal to x plus 5. And then we integrated the other direction, the x direction, from 1 to 10 because it intersected here at 1, x is equal to 1, and then it ends over here at x is equal to 10. After that, it just becomes a bunch of math. Integrate the first thing, you're integrating along y, so you're holding x constant. So this is a constant. When you integrate, you get this here. And when you evaluate the limits of integration, you've got some math here. You plug the limits in only into the y's, because that's what we integrated with respect to, and you get this basically right here that we simplified. And we continued simplifying all the way until we got this polynomial. And then you take this polynomial and you integrate it along dx from this limit here, and then you do that, which is just a basic calculus 1 integral, and you get a big fat number, 1,296, okay? So this section we have tackled a super important topic that's we're going to continue refining it and building upon it as we go off into the next section, several sections. It's called the double integral. It's not anything too terribly fancy, it's just an extra integral in there, and what you basically are doing is you're integrating in two directions. Just like we were taking derivatives, we could take a derivative in one direction and then in the other direction. Here we're actually integrating in two directions. We're sweeping out an area that we're integrating this function over. That's what we're doing. So there's always a region R in the xy plane that you care about. Please burn that into your head when you're doing these integrals. You have to think about the region R in the xy plane here. Your function sitting up above it, you're integrating this region here because that's going to define your limits of integration just like it did right here. So you do, once you have your limits of integration set up properly, you do the inside integral first, evaluating the limits of integration appropriately, and then you take that result and you plug it into the outside integral and then evaluate that one. And in that way you're able to integrate a function, a multivariable function, over two directions. And this is used in all sorts of, I mean everywhere basically. Heat flow, fluid flow, everything has double integrals all over the place. Anytime you have a two-dimensional system, it could be the cross-section of a pipe, it could be, you know, around an antenna, it could be a sphere or something around an antenna that you were looking at to see what would happen through this surface area of some radiation going through this plane or something like that. You would have a two-dimensional thing that you're integrating over, okay? And that's exactly what you're doing here. You're integrating in two dimensions. So take it one step at a time, check your work after your first integral, and then take that result, put it into your outside integral, and you'll be tackling double integrals without any problems.